All right, so the next topic here is 1.2 mass spectroscopy. And again, this is for the AP Chemistry 2020 exam prep, and we're still on Unit 1. This is the second video. This will be a little shorter than yesterday's. So, going ahead, 1.2 mass spectroscopy of elements, and this is the introduction. So, I found this visual online, and I thought that was really helpful as it can help us gather our prior knowledge and connect to what we're going to learn in the coming future. So, we have a coin here, and we see that this coin is made up of copper. And we can see that there's copper 63s and there's copper 65s. And this just means there's different isotopes. That means it's still copper, but there's a different number of neutrons. All right, so this copper has a mass of 63. It still has the same number of protons, but different neutrons. 65, same number of protons, but different number of neutrons. So, but just by looking at this, I can see there's more copper 63s than there are 65s. So this tells us that the mass of copper, because these are different isotopes of copper, right? So the mass of the actual element copper would be closer to 63 than it would be to 65, which actually it is true because the mass of copper on the periodic table is 63.55 AMUs. So this prediction is right. All right, so going forward. Now, here in this visual, my question to you would be, consider this data table and determine the average mass of this element based on this data table given with isotopes and its percent abundance. So, how would we do this? So first, we know that this is the mass, right? And most of you are probably familiar with it, but let's quickly give a quick refresher. So percent abundance is how abundant or how popular or how much of it is in nature. And here we see that neon with mass of 20 is 90.48% abundant. 21 is 0.27 abundant. And so this is less, right? So we know that this is the most, and then this is last, right? So, how do we find the average mass of neon here? So, we'll go ahead, take this mass, so 20, and we'll multiply by the percent, and convert the percent into decimal points. So here, to decimal, we divide by 100, right? So we divide by 100, we get 0.9848. We just move the decimal points 2 places, right? This way. So it's 0.9048. We multiply that. And whatever number we get, we write here. Then we do 21 times its percent abundance. Now here, be careful. It's in percent still. So you still have to move it, meaning it's 0.0027, not 0.27. It might look confusing, but it is this. Next, we'll go ahead and do 22 times now 0.0925. Now we'll go ahead and multiply all these out. So for the first one, just use your calculator. And 20 times 0.9048. Oh, this should be 0. My bad. And I get 18.096. I do 21 times 0.0027. And I get 0.0567. And then lastly, 22 times 0.0925. And that gives me 2.035. And don't worry about sig-figs as of now. Now, so here we found everything. Now, what we do is we take all these numbers and we add them. We add these, so I do my calculator. I do this, 18.096 plus 0.0567 plus 0.035, and I get 20.18 AMUs. So that's the average. If you guys think about it too, what is average? Right, average, how do we find an average of something? If you even, like most of you guys, how do you calculate grades? If you know you got the sending test and you know that's how much it affects your average, you multiply them and then you add all your grades to figure it out, right? Same thing here. These are the grades and this is how much weightage it has. So same thing, we multiply the grades by the decimal of the percent weight, what we did here, and then we add all them together to find our cumulative, which is average mass of neon. All right. So, mass spectroscopy of a sample containing a single element can be used to determine the identity of the isotopes, the element and relative abundance of each isotopes in nature. And now that may sound difficult, but it's really not. It's just basic reading graphs and doing math. So, if you're interested, what is mass spectroscopy? So, mass spectroscopy of elements is calculated by a mass spectrometer. This is a device in which we can use to find different abundances of isotopes, right? So what are the steps of it if you're interested? The first step would be electron bombardment. Second would be particle acceleration. Third is ion deflation. And fourth is ion detection. And fifth is data analysis, which is what we're doing right now. So this question here I added here tells us to find the mass of lithium here. So this is how most of your problems will be like. It'll give you these peaks, and it'll tell you find the mass, find the percent abundance, or it'll tell you do more complex problems with it. So how do we go ahead and start it out? So by looking at this, quick question. How many isotopes of lithium exist in here? Just by looking at this. If you said 2, that's correct, because we have 2 peaks here. One at 6 and one at 7. So there's 2 isotopes of lithium. Right? So looking at the graph, what masses are present on the graph of the following? So the mass of the most abundant isotope, what is that? Yep, 7 AMUs. And what about the least abundant? Looking at this, least abundant, the smallest peak intensity is of 6, so 6 AMU. Okay, so now if I say to label each peak with the nucleotide symbol of each isotope, what does that mean? That's basically use the element, then we look at the periodic table, we say, so whatever element we have here, let's say this, you could put whatever element here. Here is the number of protons / atomic number. And here is the mass. So for this lithium, the atomic number is the same, right? 3. Because that never changes. If it has an atomic number of different atomic number, it's not lithium anymore. It's a different element. The mass number here is different, right? Because this is lithium with mass 6, and this is 7. So this is pretty much what a nucleotide. Okay. Going forward. Okay, looking at this, what do you think will have a more powerful impact on this lithium's actual mass? 6 or 7? What do you think will be closer to, 6 or 7? Yeah, now if you said 7, you are correct, because there's more it has a higher relative intensity. And we can see this, it has 100, relative intensity of 100 versus just 8, 4, or 6. So it'll have a greater pull. Now, if I say calculate the average atomic mass of this element just based on this data, how would you do that? So, we can do this by this table right here. So, what we do is we say that this is peak 1 and this is peak 2. So, peak 1 percent. So how do we calculate percent? We divide part over total, right? Part, which is how part over total. So the part is 8 and the total would be what? Not 100. 100 plus this 8 because it's total, right? So 108. And we multiply that by 100 and that will give us the percent. In this case, I get 7.40%. Same thing with peak 2. Peak 2% would be part 100 over whole 108 times 100, and this would be 92.6%. So we just found the percent abundance of these two isotopes. All right? So we can see, obviously, it proves our understanding that lithium 7.3 is more abundant than lithium 3.6. And if you look at lithium's mass in the periodic table, it is closer to 7 than it is to 6. All right. So here, calculate the mass of boron. Boron 10 has 20% abundance. Boron 11 has 80% abundance. Calculate the mass of boron. And this is a different question than what's on this table here. So what do we do here? This was the very first problem we did. We did 10 times 0.2 plus 11 times 0.8, right? What is that? So 10 times 0.2, that's just straight math, 2, right? Plus 11 times 0.8, and that's 8.8. And then now we add 2 to that, we get 10.8 AMU is the mass. All right, this question is done. Now, what element mass spectrum is represented below? So what element is this? So we have 185 and 187. Now, let's look at a periodic table. What element or elements lie between these two ranges? Just by looking at it. So, we go to our periodic table. We go down to where it says 185, the range. So, the only element I find would be Re. 185, so it has to be 185 is less than this element X and it has to be less than 187. And we know it cannot be equal to because then this will be the only peak there is. There won't be two peaks. So it can't be equal to. Now, looking at it, what elements pop out to you between 185 and 187? Okay, the only element that comes to my mind is Re. It has a mass of 186.21 AMU. And that fits perfectly, right? Because this is pretty big. So it'll be closer to 187. But 185 is not that off either. Like it still has a pull, but not as a greater pull as 187. So it makes sense. 186 is halfway point, just a little bit more pull from 187, 186.21, which is RE. Alright, so that's it for this video.